मच रही है और वो बनकर एक्वागार्ड का
Hey, Pipan. Hey, Rathi.
Good afternoon, Shajesh.
Good afternoon. Good afternoon. How are things?
Yeah. Okay. How are you?
Yeah, I'm fine. So this is going to be the continuation of uh, the first part of the talk was what happened before the Big Bang. So it should be at
Interesting.
a popular level. Yeah, it should be interesting for everyone. I guess all of us ask these questions sometime in our life.
Isn't that the first one Bipin attended?
Yeah. I attended that.
Then it got like disrupted. The middle.
Shajesh, I just wanted to know one thing before you start this thing.
Yeah, go ahead.
Assuming that we say that our Earth is a sphere, like, so if I drill a hole here, so where will it? If I drill a hole here, so where will it? Suppose what will be the outlet like?
If you go exactly through the center of Earth, in the theoretical sense, you will come out on the other side of the diameter, which for India might be, I wouldn't be surprised if it is somewhere in the Americas, either North or South America. South America,
No,
probably, right?
But how it can be like if I jump into that, and will I come out? Because if you say gravitational force, so will that?
So theoretically speaking, that's a correct question to ask. Theoretically speaking, now it's a different matter that right at the center of Earth, it is too much of lava there. It's not solid. But pretend that there is a pipeline there, which is strong enough that you can go through. Only gravity taken into account. It's very interesting. You can reach the other side within about 42 minutes.
Okay.
So you can do this calculation. It comes out. If you assume the Earth to be perfectly uniformly dense, then it comes out 42. But with more realistic considerations, it comes out about 38, 39 minutes. So it's an interesting calculation. Is that the question you asked?
Yes, I just wanted to know can it be like what I'm thinking is it real to something what I'm thinking, like, because if you say that Earth is round, and if individual bore a hole over here, so as per the gravity he should not come out from the other end. As per the gravitational force, he
Yeah,
should not come out from the other end. If you but they say that in the crust of Earth there is lava, and that there is gases, something like, where gravitational force is not acting, like not working
no, that is not the
in the
reason.
core of in the core or in the core of the Earth.
Yeah. I mean, think of, you gain so much velocity there that it takes so much time to slow down. By the time you slow down, you reach the other side. Do you see what I'm saying?
Okay. Yeah, okay.
Like you pick up speed. So at the center of Earth, ideally speaking, if you were at rest, you would just stay there. But by the time you reach there, you pick up so much speed that you keep going across on the other side. Yeah, it's interesting. Yeah, we should maybe sometime have a small talk or something on
This is okay. This is more related to geography or physics, somewhere
no,
physics.
just gravity, pure gravity. If you assume pure gravity, that's what would happen. But realistically speaking, can you dig a hole in the earth? Probably we have only dug about few kilometers. Earth is about 6,500 kilometers, and we have been able to
Okay.
dig only maybe 5 kilometers. So it is nowhere
Okay.
close to reality.
Okay.
So it's a theoretical calculation, but a interesting theoretical calculation. Yeah.
Okay.
Okay. Yeah. Yeah. But yeah, good point. Good question. Yeah, maybe I will sometime we will discuss this here in this platform. Maybe yeah, it's a good question to ask for youngsters. Yeah, and maybe or whatever you're saying, all that can be addressed.
Mm.
Hello, Rathul.
Hi, Sudesh.
Yeah.
Can you hear me?
Yes, I can hear you. Yeah, nice. Thanks. Yeah, thanks for continuing on this. Yeah, we look forward to this. It's
Yes.
interesting
So,
topic.
yeah, I wanted to give this a couple of weeks ago because I was not well last week, and last month I was a little bit busy. And
Yeah. But now everything going good, right?
I'm not completely okay.
Uh-oh.
Throat pain and chest infection little bit.
Oh, not good. Okay.
Yeah, some kind of virus is attacking.
Yeah. Like these days, everywhere it's, and it doesn't help that you have the COVID around, and that raises social concerns. Yeah. I just came to know yesterday that I had gone to a gathering. Basically, it was a students' gathering. I think I put some pictures of that 10 days back. There was an event of a gyroid, and one of the kid there had COVID, and it spread to all the kids apparently. So I was I was left alone, I guess, because I didn't interact too much with kids. They were all assembling that. So just yesterday I came to know about it from a parent that many of them were having it. So it happens, yeah.
So this happened in Kerala. Where is that?
No, it was here. It was here after I returned here last 10 days or so. So
Okay.
so yeah, so it's still spreading, but nothing like most of them were vaccinated. So it was okay, I suppose. But still, there is a lot of fear associated with it, I guess. But in my understanding, I think it seems like if you're vaccinated, you are reasonably okay.
Yeah.
Let's see. Okay. So it's 5 minutes past 3 in India. So shall we proceed, Rathul?
Yes.
Yeah.
Okay, I will share my screen.
Okay, go ahead. Yeah. Yeah, go ahead, Rathul. So just to give a formal introduction, Rathul gave the talk on, oh, just give me a second. Hello? You can just join without logging in, right? It is kvshailesh@gmail.com, but you don't need to log in. Yes. Yeah, I'll send it to you. Okay. Yeah, I was just introducing, and I'll send it to you in a minute. Okay. Okay. Yeah. Sorry, I picked it up because they are from Sphics. So I just wanted to make sure that so they are also logging in. So give me a minute. So
Yeah, sure. So what time is the?
Oh, in US it is it's 4:30 a.m. Yeah.
Yes.
Yeah, so it's pretty early. Yeah, but in Sphics it turns out to be a reasonable time, right? So that's right. So I'll just introduce Rathul, and then you can proceed. Then I will give the link to them in a minute or so. So again, Rathul gave the talk on what happened before the Big Bang, and this is a continuation of the talk, and we look forward to the discussion. Thank you, Rathul.
Yeah, okay. Then can I start?
Yes, please. Yeah, I'll take a minute and I'll give the link and come back. Yeah, go ahead.
Okay, so the last time we had discussed about hot Big Bang model, and we discussed that this is a broadly accepted theory for the evolution of our universe, the origin and evolution of our universe. According to this theory, the universe had started as a very hot, dense soup kind of matter, and then it expanded and cooled to its present state. We also discussed that this theory, this hot Big Bang theory, is based on two key ideas. One is general theory of relativity, and another is cosmological principle. This cosmological principle is just the assumption that the universe is homogeneous and isotropic on the large scales. And from large scale observations and also from the CMB observations, we are almost sure that this cosmological principle is not just an assumption, this is a fact nowadays. And yeah, that's what we have discussed last time. So from observations, we currently know that our universe is largely made up of three kind of fluid. One is dark energy. The current universe mostly dominated by dark energy and dark matter, and also a little bit of radiation. So according to the theory of hot Big Bang theory, the universe had started as a soup of relativistic particles. We can call it as a radiation. And then the universe got expanded, and the universe became matter dominated. And currently, the universe is mostly dominated by dark energy. Okay, so that is the hot Big Bang model of our universe. And not only that, this hot Big Bang model also predicts a kind of thermal radiation. It's almost isotropic. It means from all the directions we get same intensity of radiation called cosmic microwave background radiation. So hot Big Bang model predicts this kind of background radiation. In 1965 or so, this kind of cosmic microwave background radiation was discovered, and the discovery of this CMP and also the discovery of the expansion of the universe had led to the theory of our Big Bang model as a viable model of our universe. But it's not a perfect model actually. After this, the discovery of this cosmic microwave background radiation in 1965, there were other kind of observations made on this cosmic microwave background. As I said, it's a homogeneous background radiation as expected from the Big Bang model, but we see that from the observations of Kobe and WMAP, and also from Planck recently, that this cosmic microwave background is not actually very homogeneous. It's actually has small fluctuations on. Means in a different directions. When you measure the background, see CMB radiation from different directions, you measure different temperatures. It's very small actually. These fluctuations are very small. It is around 1 by 10 to the 5, that kind of small fluctuations. So according to the hot Big Bang theory, this is not expected. Okay, so I mean, hot Big Bang theory couldn't explain why this kind of small fluctuations present in the cosmic microwave background radiation. And also it is known that these small anisotropies in this cosmic microwave background evolve and form the large scale structure that we see today. Okay. So the hot Big Bang model, the standard hot Big Bang model, didn't explain why why these fluctuations are generated, or how these fluctuations are generated, and how these fluctuations eventually evolve into large scale structures. So that's a kind of a major drawback of this hot Big Bang model. Okay, so that is one of the questions we can ask about how these fluctuations are originated. And so according to this hot Big Bang theory, as I said, we know the physics from a certain point of radiation dominated epoch. From that we know how the universe has evolved from that point. So before that we don't know. So we expect that this kind of fluctuations are originated somewhere in the very early universe. I mean, even before the radiation dominated epoch. Okay. So we have to go beyond the standard hot Big Bang model. Okay, so I think this is clear. So the one of the very first attempt to solve this problem of generation of fluctuations in the very early universe is made by these people, Alexei Starobinsky, Henry Linde, Paul Steinhardt, and Alan Guth. So these people proposed that before the radiation dominated epoch in our history of universe, there was another epoch called inflation. Inflation is basically a nearly exponential expansion of the space. So suppose we fix this kind of epoch in the very early universe before the radiation dominated epoch, we can solve some of the problems of hot Big Bang model. Mainly, we can solve, or we can explain the origin of structures or origin of anisotropies present in cosmic microwave background radiation. Okay, so inflation is the modification done on the standard hot Big Bang models. Now the theory is for inflationary cosmology or inflationary Big Bang model, you can call it that. It's not no more standard hot Big Bang model. Okay, so any questions so far?
No, good.
Okay. So according to this theory, or according to inflationary cosmology, the structures or the fluctuations in the CMB that is eventually evolve and form the large-scale structures like clusters of galaxies, clusters of galaxies, and other structures in the universe is originated as quantum fluctuations. Okay, when the universe is very small, these quantum fluctuations during inflationary epoch, these quantum fluctuations got amplified and leave its imprint on cosmic microwave background when the universe evolves. Okay. So that is the current picture of this formation of structures in the universe. Okay. So yeah, so this is what happened before the radiation dominated epoch. So this is the modification of the hot Big Bang model to accommodate this formation of structure in the universe. Yeah, but there are problems. It's not very perfect theory. The inflation is the most popular modification of the standard Big Bang theory. That is true, but there are problems with inflationary model also. The main thing is we don't know what drives inflation, which means we know that from the observation universe contains radiation, matter, and also dark energy. But usually the inflation is inflation is constructed, or inflation is obtained with the aid of scalar fields. Okay? So we don't know what kind of scalar field, or we only know the Higgs field, but Higgs scalar is Higgs inflation, or basically means the inflation is driven by the Higgs field, is not a very viable model of inflation, so it is almost discarded. So we don't know what exactly drives the inflation. So that is one of the main drawback of inflation theory. And also, what causes inflation? I mean, what is the initial condition to start the inflation? That is another problem, inflation. And also there is a problem with the stopping of inflation. Like when inflation stops and how that happened. There are theories, there are postulations, but there is no very viable model for the ending of inflation so far. And also, what happened before the inflation? That's also very important question to ask, because if you go back in time before inflation, the space can go into a singularity. So singularity is still a problem in this inflationary cosmological model also. So these are the main problems of inflationary cosmology, but this is very successful in explaining the structure of our the structures in our universe, like the large scale structures, the origin of galaxies and clusters of galaxies in our universe. But the inflation, yeah, it's a popular and well-studied model of early universe, but there are other models like bouncing scenarios. It suggests that the universe is not simply started from a point, but our universe is basically a part of a cyclic universe, which means there was a contracting phase prior to this Big Bang event. We can call that's not exactly the Big Bang, but there was a contracting phase, and that contracting universe reaches a minimum value, minimum size, and then it expands and becomes our kind of universe. Okay? So that's called bouncing scenario, bouncing model or scenarios, you can call, and there can be different cycles in prior to this prior to our universe. Like there were lots of this kind of cycles happened before the Big Bang. So the main scientists behind this model are Neil Krog and Steinhardt. Actually, Steinhardt was the first proposed, or the Steinhardt is basically the main supporter for the inflationary paradigm. But now he is thinking the inflation is not a correct or viable model, but now he is working more on bouncing scenarios. He thinks that the bouncing scenarios can be more viable, or it has more predictable power than the inflationary scenario. And also Roger Penrose, you people may know him, he got a Nobel Prize in 2020, and he also has a very different kind of bouncing scenarios. And Abhay Ashtekar, is an Indian, and he has a bouncing scenario model which is based on loop quantum cosmology. So these theories or these scenarios or these models are also predicting the formation of structures in the universe as inflation does. So these are also viable and popular models nowadays. Inflationary models and also these bouncing scenarios can consider are the viable models of the universe in the context of formation of structures in the universe. So far these are all postulates or these models have advantage. Some models have some advantages, but there are drawbacks also. So as I said, the bouncing universe is basically there is a contracting phase, and during this contracting phase, as in the case of inflation, there can be quantum fluctuations, and these quantum fluctuations amplify during this contracting phase, and it goes through the bouncing phase, and it leaves it imprints on cosmic microwave background radiation, and that fluctuations eventually lead to large scale structures that we have seen today, that we see today. So that is the formation of that's the theory of formation of structures in bouncing scenarios. Yeah. So according to inflation, these quantum fluctuations are generated when the universe is very small, but here the fluctuations are generated during the contracting phase. The universe may not be very small. Okay. So there are problems like still, even in the case of cyclic universe, the singularity is still an unsolved problem. So if we go back in time, the universe, the universe goes into a singularity. So we don't have a correct theory for resolving the singularity so far. And there are theories or postulates saying that there can be Planck scale effects, and we have to consider the quantum gravity effects when we go to very small scale. And so we don't have the correct theory for the quantum gravity yet. So yeah, it's still a mystery what happened in a very small universe. And the another problem, as I mentioned in the case of inflation, the bouncing phase or the contracting phase, we don't know what drives this contracting phase or bouncing phase, because the usual matter cannot drive bouncing phase, because it's we need some kind of exotic matter. Like people say that we need some kind of matter which violates the null energy condition, where the sum of energy density and the pressure should be negative. So we don't know such kind of matter in the universe. So we need some kind of exotic or ghost-like matter to make the contracting phase. And there is another problem, as I said, there are postulates, like, but still it is not a solved problem. Like these fluctuations are originated as quantum. So what we see or we measure the fluctuations in the universe, or we measure the correlations of different galaxies, or the correlations of temperature in the cosmic microwave background radiation with classical instruments, or we treat the correlations or study the correlations with classical distribution functions, right? So, but these theories predicts that these fluctuations are originated as quantum fluctuations. So, how these quantum fluctuations transform to classical, how this became classical? That's one of the main issue. And if these fluctuations are quantum in nature or quantum in origin, then how can we detect that, or how can we justify that these are quantum fluctuations? That is one of the open problem cosmology. And still, as I said, what happened before inflation, what happened before the contracting phase of cycling universe? So how this inflation or contracting phase started, means what are the initial conditions? So these are still an open questions. And how can we distinguish, because this inflationary theory and bouncing scenario both predict similar things. I mean, both predicts how the anisotropies in the cosmic microwave background are generated and also predict the correct distribution in the cosmic microwave background radiation. It's nearly scale invariant in the sense that anisotropies, when we analyze this anisotropies in the cosmic microwave background or the fluctuations in the cosmic microwave background, when we write in the Fourier space, we see that for all scales, the amplitude of fluctuations are almost the same, okay, which we call that scale invariant. So this kind of property is predicted by inflation as well as bounds. Okay. So, I mean, these are both are viable models of early universe. How do we distinguish these? So we need more kind of probes or observations to distinguish these theories. And recently there is another interesting question, like you know that I think in 2015 or so we detected the first gravitational waves from the binary system, binary black hole system. I think it's one was the black hole and another is the neutron star. And after that, we have detected hundreds of other signals also. But some people suggested that these black holes that we have detected through these gravitational waves may not be astrophysical, in the sense these black holes cannot be formed from the collapse of astrophysics, collapse from the stars. Okay, so it may be formed from some early universe scenario, like it can be formed during the radiation dominated epoch of the universe. Okay, so inflation predicts such kind of formation mechanism for the primordial black holes. And also people are interested in these primordial black holes because these primordial black holes can be a candidate for the dark matter. So so this dark matter, we know that we don't know what exactly this dark matter can be, some exotic particles, but we know the dark matter only through its gravitational interactions. So this primordial black holes is a perfect candidate for this kind of gravitationally interacting particles. So some of the fraction of dark matter or the complete distribution of the dark matter can be primordial black holes. And there are mechanisms in inflation and also in bounds to produce this kind of enough number of primordial black holes during the early universe. Okay, so yeah, I mean, I have just listed some of the popular books people can read to know more about cosmology and hot Big Bang model and also the inflationary cosmology. The first 3 minutes, it's a book by Steven Greenberg, and it's about the hot Big Bang model and also the brief history of time. These are the popular books, not very technical, but very interesting to read. And there are technical books by some people, like undergraduate textbook. I just listed some of them, but there are more. Okay, and also recently there is a lecture notes on cosmology by David Tong. Very interesting, very intuitive, and people can go through these lecture notes also. So David Tong has variety of lecture notes on various subjects, various topics. Its lecture notes are very famous, and yeah, people can go through this, and it's very interesting. So that's it. I mean, that's what I wanted to. It's very short because I already talked about this hot Big Bang model the last time. So I'm sorry that it's
No.
so short. We can have more questions. That's
yeah. Questions? I have a question. So we have James Webb Space Telescope out there.
Yes.
Can it? Is there any chance that it can throw light on whether it is bouncing, whether our universe is bouncing or inflating, or it is?
I don't think so, because this James Webb telescope is basically for studying the galaxies and more on astrophysical purpose, right? And so maybe we can get the correlation functions of galaxies, and uh, but what we need is more information from the cosmic microwave background radiation to understand the very early universe. So because mm, very almost the information is lost when we come to the current universe. So it's very difficult to understand the very early universe from the current epoch. And if we can detect cosmic microwave background with more precision, and if we have some kind of gravitational waves from the very early universe, we can detect the gravitational waves from the very early universe. That also can lead to a very good probe for what happened before the Big Bang, or what happened during inflation, or whether the correct scenario is inflation or bouncing scenarios. There are proposals for that.
And would you? I always thought that the cosmic microwave background was reasonably precise, like very precise, in fact. But you would, or if we have, let's say, next to uh,
Mm.
modes, even then uh, this will not be sufficient. Is that the point?
Okay, so this is precise, but so far what we know is two-point correlation functions. Okay, so with these two-point correlation functions can be modeled or can be described with just three numbers. So these three numbers are not sufficient to distinguish between this inflation, or distinguish among the inflationary, I mean, to screen some of the inflationary models. There are varieties of inflationary models, more than thousands of models, I can say. So these all predict similar values for these three numbers. Okay, so what we need to go beyond, like beyond the 2-point correlation functions. We need 3-point correlation and 4-point correlation and more. For that we need more accurate probe or observations, and also we need more sensitive observations to detect the gravitational waves from the CMB. There are effects from the gravitational waves on the cosmic microwave background radiation. Okay, so to detect that, also we need more sensitive instruments.
And Big Bang is expected to have lead to a gravitational wave, correct?
Yes.
And will it be
Okay, so
stronger or weaker than the galaxy black hole we have?
it is very weak. It's very
Very.
weak, and it's very difficult to detect. The Big Bang, as I said, is a very bad name, because okay, so I think what you mean is the gravitational wave is generated during inflation. So during inflation, of course, as I said, the fluctuations in the CMB are generated, and at the same time, the gravitational waves are also generated. Okay, during inflation. I mean, these during inflation, in the sense, these are all quantum fluctuations. These were all quantum fluctuations, and then it became classical during inflation. Okay. So at the same time, I mean, the scalar fluctuations, scalar in the sense that the cosmic microwave fluctuations were generated at the same time. Gravitational waves were also generated as quantum fluctuations. Okay. So these quantum fluctuations are very weak. the gravitational fluctuations are very weak. But there are indirect effects of these gravitational waves on the CMB that we haven't detected yet, and also there are direct we can detect this gravitational wave directly also. That also we haven't detected because that's very weak and needs more sensitive instruments.
So one more question. So when we think of quantum fluctuations in that era, is it quantum fluctuations in the electromagnetic radiation, or is it quantum fluctuations in the gravitational field, let's say? So is
Okay.
it gravity? Where is gravity in that picture? I understand radiation and matter, but where is
Yeah.
gravity there? Gravity is also
There is,
involved in it, right?
yeah, gravity is also involved. Gravity is everywhere, right? I mean, even
Correct.
before. Okay, so according to this inflationary theory, what drives inflation is some scalar field. We don't know what exactly that scalar field. So it is some energy, and that energy fluctuates, or the scalar field is a quantum field, and that quantum field fluctuates, and that fluctuation leads to fluctuation in the space-time, right? So it both fluctuates, the scalar field and also space-time, and both evolve, and that leave imprints on cosmic microwave background as scalar fluctuations, I mean the scalar field fluctuations and the gravitational wave. Gravitational waves fluctuations, what I mean is the fluctuations in the space-time or the space.
Got it. Got it. Okay. Okay. And it is radiation dominated, or is, like, I understand before CMB that it was radiation dominated.
Yeah.
But
So
is there any
before
point
that,
during inflation?
yeah. So during inflation, what we assume is scalar field dominated,
I see.
not the radiation, because it is before the electroweak transition, right? There we don't know the electromagnetic. There were no electromagnetic fields, right? It is before the electroweak transition. So I mean, all the forces, like except this gravity, we assume that it were combined to form one force. We don't know what it is. So we can say that the relativistic particles were there, but during inflation, our assumption is that the scalar field is dominant.
And
But
we
there
have
are
no hints of.
postulates.
Yeah, go ahead.
Sorry.
Go ahead. Go ahead.
Yeah, but there are postulates like we don't need scalar field to generate inflation, but electromagnetic field or electroweak field or some other kind of but particles with spins can also generate inflation. But the popular and the simplest way of achieving inflation is with the aid of scalar field, and that is matching with the observation so far.
Got it.
You may have mentioned it and maybe I missed it. So what is this scalar field actually related to? I mean, what's the most likely candidate particle
Okay,
for it?
so this scalar field, okay, what we know or what we have detected so far is just this Higgs particle. We know the Higgs particle. It's an excitation of Higgs scalar field, right? So we know only that scalar field so far. But the problem is there are attempts to construct inflationary models with Higgs field, but a canonical, but with canonical Higgs field, we cannot get a viable inflationary model. So it is inflationary scalar field is something else. We don't know yet what it is. Yeah, it's,
So
it's a kind of a new particle introduced, but we don't know what exactly it is.
new particle introduced, yeah. And
Yeah.
like the point is like, what about, so as you were saying, like there is only one detection that has been done. So is it expected to be present even today, or like it probably
No,
was in the early
actually,
universe and gone?
yes. So yeah, this is that scalar field was dominated during the inflationary epoch, and that scalar field actually decays. The theory is the scalar field decays to form other standard model particles at the end of inflation.
Mhm.
So it has
Basically,
to have a
these,
mass then.
yes.
So it is not massless. It couldn't have been
It's
massless.
not, yeah, it has a mass and it decays. I mean, that's the theory of formation of the standard model particles
Got
from the inflationary, in the context of inflationary theory. So this is how the standard model particles are formed. It decays or it is formed from inflationary scalar field.
Mhm.
For some of the particles, maybe not the complete standard model particles, but some of the particles.
Got it. And you showed the fluctuations in density is 10 raised to minus 5. That is based on the anisotropies in CMB, correct?
Yes.
Is that the correct conclusion? And this is
Yes.
precisely measured, right? Which
This is
means that
precisely measured. Yes.
okay. And you also suggested in the early part that this was not expected. Is that like in the hot Big Bang? Is that
Well, we observed this, but the problem with the hot Big Bang model doesn't have any proposal for this. How these fluctuations are generated.
okay.
I mean, this is already, we know that these galaxies and all these things we observe. So we know that these structures are somehow generated in the very early universe, but the problem is in the hot Big Bang model, there is no explanation.
And why not? Just curious. Can you?
I'm why not? I didn't know.
Or maybe
Suppose
my
it's a kind of initial conditions.
okay.
Like in the hot Big Bang model, what we give is this what fluctuated universe as the initial condition. Okay. Universe with fluctuations as the initial condition. Once we put this as an initial condition, then the hot Big Bang model says that how this evolved.
Or maybe my question can be like, since we see our galaxies today, which is an anisotropy, is there a prediction as to if you make it go backward, evolve it backward, there is a fluctuations in density you can estimate, and is there any mismatch there?
No. What I am trying to say, that no, there is no mismatch. We can measure that, and we measure in CMB. Well, my point is that hot Big Bang model cannot go beyond some point. So during this radiation dominated epoch, so from at some point of time, the hot Big Bang model starts. Okay, so there we have to assume that it has already fluctuations. The universe had already fluctuations. It is very large scale. It is homogeneous and isotropic, and it had some fluctuations. Once we start with that universe, then the hot Big Bang model says how this universe evolved.
Yeah. And is there any meaning in talking about the fluctuations in the dark matter versus dark energy versus radiation in this? Can it be divided into three, or is it always total we talk about?
Okay, so during inflation, there is only one scalar field. So the fluctuations are only in the scalar field. So at the end of inflation, these fluctuations are transferred into the fluctuations of different components in the universe. So there are fluctuations in the radiation, matter, and dark energy, and these evolve separately. I mean, these are all combined in the sense that these are all fluctuating on the background of gravitational field. Right? I mean, the gravitational field also fluctuating.
So maybe you can comment on one more thing. So you are basically starting from like sometime after the well, as we say, it's a misnomer, but after the Big Bang, right?
Okay.
Like this
Yeah,
discussion that fluctuation in a scalar field occurs and inflationary period happened. Like this is something like not right at t equal to 0.
yes. That is
It is
true.
like sometime after. So is there any I mean, what's the word for the period before inflation up to t equal to 0?
Actually, we don't know what happened before this inflation, or we don't know when this inflation started. But there are proposals by Stephen Hawking and Hartle and Vilenkin. These people had proposed some kind of wave function of the universe. So it's a quantum mechanical or quantum field theoretical view of universe. There, the proposal is the universe had started from nothing, which means there is a probability for universe to start from nothing if you consider some kind of wave function. Okay.
Mhm.
And also this theory, I mean, there is a, I mean, from this proposal, of course, universe can start from nothing. That universe can be anisotropic or inhomogeneous, what all it can have. But then after suddenly inflation started. But these are all proposals. Like we have different ideas and proposals, but we haven't tested or we haven't got any observational predictions from this kind of models.
Mhm.
Yeah.
Like, I mean, normally the like mental picture one makes is that, oh, there was all energy sometime. And then now at inflation, you are already bringing in a fluctuation in scalar field, which is related to some massive particles. So somewhere the creation has already begun, right? Like,
Yes.
so, yeah, I mean, yeah, that is what I was like trying to relate it with, like, maybe one can say, oh, where did this scalar field actually originate from? Like, what was it? What's the source of that?
Yeah, we don't know. That's the answer. I mean, nobody knows.
Yeah. And that's okay. That's why I said, like, what's the word? Like, people, do they ask the question or not?
Yeah, of course, people ask, but we don't know and we don't have any correct answer.
Mhm.
Yeah.
So we have during supernova explosion, there is a huge change in the configuration of the, let's say, a star, correct? So can such just simple elastic collisions be a factor in this Big Bang, or is it just not at all
So I
viable?
didn't understand.
Like during an explosion of a supernova, basically they collapse into the center, and using elastic collision, we say that, oh, the outer part of the star is exploding out, and that happens very fast, as far as I understand.
Okay.
So similar model can it be used to explain Big Bang, which is very simplistic probably, but why can't we just? Is there any simple explanation why we cannot use that?
Sorry, I am not able to imagine that how this is related
Probably
to how
not,
can
right?
we connect this to the Big Bang. One thing is this is a very high energetic epoch in the sense it is even beyond the electronic transition scale, and there were no kind of radiation or electromagnetic field there, and I don't know how we can, and this is, I mean, the model, inflationary model is simple. I mean, it's not very complicated. We use scalar field that can drive the exponentially expanding space, like today we know that the universe is expanding so far, so it's acceleratory, sorry, it's an accelerated expansion, right? So that is due to dark energy, and we don't know what exactly dark energy is. Similar way, the very early universe, or the before the radiation dominated epoch, universe was expanding exponentially, and we don't know what it was. We don't know what drives that exponentially.
Okay, okay. And again, there is no observational evidence of anything beyond CMB, CMB epoch, right? Or is that what it's
Yeah,
called?
yeah, that
No
is true. That
observations, right? Beyond.
no observations. Yeah, this is the phase we can see.
Mhm.
I mean, directly through the satellites or the observation, it's called the telescopes. And but as I said, during inflation, the gravitational waves can be produced, so that we can detect. Maybe we need more sensitive instruments. So far, we could go only up to this point. So this CMB is actually formed or generated, I think, some few 100,000 years after this inflations had started. So that is the time we could go so far. Okay. But there were neutrino were produced even before that, but detecting neutrino would be very more difficult task. So we don't know, and we don't have uh, an experiment set up to detect those neutrinos, some primordial neutrinos, people call it. Yeah,
And where does Casimir effect fit in to this? When
that I don't know.
no. Okay. Okay.
Vacuum energy. So maybe like slight digression again a little bit. So inflation was introduced to explain the expansion, right? And the acceleration.
No, actually, inflation is the accelerated expansion. We didn't know that there was a kind of accelerated expansion in the early universe. We need that accelerated expansion to solve some of the problems of hot Big Bang model. Like we need to explain the origin of these structures, and also there are some problems like horizon problem and flatness problems. I didn't mention all these things, but there are some more problems on this hot Big Bang model. So to solve that, we need an exponential expansion of the universe. That is called inflation.
Yeah. Okay. So is there is there anything alternative theory to inflation?
Yeah, that's what I said.
Bouncing,
That
yeah.
there is a bouncing scenario. So there we don't need an inflationary epoch. So just fit the. Okay. So we know this from this hot Big Bang model. We know that the universe had started from the radiation dominated epoch. So the bouncing scenario, what it does, it just fits a contracting phase just prior to this radiation dominated epoch.
Hmm.
Okay. Then
Yeah, but then why it is not like after it fits at that location, after that, why doesn't it follow the description that is in the hot Big Bang model and inflationary model? So
then we don't need inflation. So there is a contracting phase, and then after that, after this contracting phase reaches the minimum, then the hot Big Bang phase started.
mhm. Yeah, I guess
Does it answer the question?
I'm just trying to imagine, like, if all my initial condition are same at that red epoch,
Mm-hmm.
then what is the, how one can differentiate between a Big Bang is starting from a singularity versus like oscillatory, like crunching and
Yeah, I mean, yeah, that's a problem. Like, if we provide some kind of initial conditions here with different scenarios, then we cannot really distinguish what was the scenario behind this point. Yeah, that is true. We need some kind of
or maybe
different
maybe I
predictions.
should ask it this way, like, why does bouncing scenario get away with the inflationary model? Like, maybe
Okay,
that's
so
the appropriate question.
actually, this inflationary scenario and bouncing scenario both predicts nearly scale invariant power spectrum in cosmic microwave background. That is at the level of 2-point correlation functions. Okay. But
Mhm.
when we measure or analyze 3-point and more higher order correlation functions, there are differences in the predictions from these scenarios.
Two models.
That is one way to distinguish whether the early universe scenario is inflation or bouncing scenarios. And there are other screening process, like inflation predicts some amount of gravitational waves. Okay, but some models of bouncing scenario predicts there is no gravitational waves. I mean the primordial gravitational waves. So in that way also we can screen some of the models of bouncing scenarios and inflationary scenarios.
Mhm.
Yeah.
Okay, one more thing, maybe, like, again, I'm jumping from here to another topic, like after inflation, right? You said this scalar field is going to decay into the other, like whatever is observables in today's universe, right? Basically. So what we are saying is that, like, there was something which is like just one type of interaction, which is probably at the start of the inflation, is it? Like I think I'm just trying to understand it in terms of, like, we say there are 4 fundamental interactions. We try to combine them into like some single theory of everything, and which is not, like, I mean, yet achieved. So I'm just trying to understand in the sense of, like, where is this origin of all 4 are? Like, is it at the starting of this point? It is before that? Like the 4 interaction that we talk about, like, did it start like right at the Big Bang? Let's assume that Big Bang is the origin. That's where we had like distinction between all 4 of them, or no, there is no distinction at that point. It happened after.
Okay, and so where this electroweak transition or that is actually still an open question, like where exactly this happened. There are proposals like this started after inflation, like all the particles like bosons, like W bosons or whatever the combined particles, the particles associated with this combined force are produced from inflation, sorry, from this inflaton and inflationary scalar field. There is an epoch called, after inflation, there is an epoch called reheating. So that is where this particle production happens. Okay. So there is all kind of particles that is needed for this the those are the, I mean, that is the gauge bosons that is associated with these forces originated during that epoch. It's called a reheating, or there is another small epoch called preheating. So during these epochs, just after the inflation, these kind of particles are produced, and these particles are associated with this kind of forces.
So it will, one would say it is after the
After,
inflation.
yeah, after, yes.
Mhm. I guess I think
these are just proposals. These are just proposals. There are inflationary models for the lower states. And we know where the electroweak transition happens at what energy scales. We know that. So, but there are inflationary models that inflation happens with even lower energy scale. So, I mean, that also predicts like some kind of some predictions, and that is also consistent with observation. So, I mean, these are all, I mean, proposals and not very confirmed ideas.
Mhm.
Yeah.
So just one more question. In the higher order correlation functions, can they not be written in terms of 2-point correlation functions?
If the correlation function, sorry, if the distribution function is Gaussian, then yes, but for non-Gaussian distributions, it is not possible, right?
So it involves another assumption that it is not
Gaussian.
Gaussian. Okay. Got it. Any more questions?
Well, like rest everything is like, these are vague things, right? I mean, the point will be, okay, inflation happened, then scalar field decayed, then like most of the things that we know today probably came into existence. And the point is, like, I mean, there are obviously, like as you were saying, like these scalar fields most probably created the dark matter and dark energy also, right? And that is something we do not know about it, and we are still dealing with it in the umbrella of the four forces, like four interactions.
Yeah.
So I think like something of like, oh, what is the most popular candidate or theory behind, like, oh, how will you describe these stuff? Or if people are like just going out of the box and thinking completely differently to explain dark matter, dark energy. But I think that's a digression. That's not exactly your talk. So
yeah, I mean, as I said, these are proposals, but these are consistent with observations so far. So maybe people have more exotic ideas or some very different kind of ideas. There are, like in Roger Penrose has a very different kind of cyclic universe, and the inflation is not needed, and it's very completely different from standard cyclic scenarios. But the problem is it's very complicated model, and not many people are working on it. But it predicts some kind of very different. I mean, it's giving some very different predictions other than the scale invariance of cosmic microwave background radiation, and also it's very difficult to detect also. So there are different ideas, proposals, and predictions, but with coming experiments, uh, there are experiments like Euclid, and there are experiments from like from India also. They are proposing one mission for CMB Bharat. So from these experiments, we may get more precise data and more data from different spectrum. Maybe then we can screen or distinguish these paradigms or scenarios in a better way.
And you would still say we are consistent with the observations, even though we do not have dark matter, we are missing dark matter and dark energy. We would still say it is consistent, right? Because you're saying they predict
Which
that number.
oh, I didn't understand. So actually,
Like, would it be correct to say that we are consistent with the observations when we are actually missing dark energy and dark matter that's in the model?
yeah, we are almost sure that there are dark matter and dark energy, but there are alternate theories like modified Newtonian gravity theory that just uh, modify the gravity, says that you don't need any particles, but just to modify the theory to accommodate this observational effects. But we are almost sure that we need particles like dark matter particles, and it can be primordial black holes. That is predicted from inflationary theory, and that is a candidate for the dark matter. And we don't know what is dark energy. That is an open question. Like we don't know what exactly it is. And yeah, from the CMB is consistent with the inflationary idea of inflationary cosmology. I mean, the inflationary cosmology is consistent with the CMB
Correct.
and also the observations from large scale structures. Yeah.
And how easy is it to change the like metric that is used to evolve the CMB model, right? We evolve it using our, like say, FRW metric. Is it possible that we can change that and still get some other configuration? Say there is no dark matter or dark energy. Is that a possibility at all?
That actually, I don't know. Is it possible to describe dark matter and dark energy by changing the metric? Hmm, that I don't know. But to change the metric, we need some justification, right? And why would change the metric? Right? The metric is introduced or constructed from the assumptions of FRW. Is basically we assume that the universe is homogeneous and isotropic.
Correct.
From that assumption, we get the metric, and we can just relax that if universe is not isotropic, then we have anisotropic models, and people work on anisotropic models and different predictions on very large scales, and there are constraints on such predictions. Yeah, people do that, but I am not aware of models saying that the dark matter and dark energy are simply some geometrical modifications. Yeah, this MOND is saying something like that. So it's a modification of Newtonian gravity. The dark matter is simply the modification of Newtonian gravity, but I don't know whether that is applicable in the case of cosmology.
Correct. Like I was saying, when we say it is homogeneous, that's an assumption, right? What if there was a anisotropy in the sense of huge anisotropies introduced? Like there is a lot of dust, if I understand correct, right? Is that what is called dust, like space, the remnants of a galaxy? Like, do we account for that? Probably, yeah, those are all vague.
Uh,
But still.
I don't know. I mean, the homogeneous, in cosmology, what we mean is around 100 megaparsec or so. Like beyond that scale, the universe is
I see.
almost homogeneous.
So we do keep that scale in mind. Yeah, and it is homogeneous. I agree.
Yeah.
Yeah, makes sense. Okay. More questions?
Well, I mean, yeah, I think it's like more of a, what do you call it? I mean, he has explained the stuff that is probably the mainstream accepted thing that is happening and consistent with whatever observations that are happening. So yeah, rest everything, like if you go around it, those are like just, touching upon what if scenarios. What if this, what if that?
So do you expect something remarkable to come from James Webb Space Telescope in the next 10 years? Which can throw light into this discussion?
I mean, I am not expecting anything very relevant for cosmology.
Got it.
I don't know much about James Webb, what they are expecting, what their intention, but there are observable we are expecting, and we are like there are some experiments or telescopes we are expecting to be launched soon, like Euclid, as I said, and
Got it.
CMB Bharat. And there are other, I think there is another Planck mission, but some modified Planck mission. Yeah, and there are other ground-based detectors, like they are planning to detect the CMB, like not the temperature prospect, temperature correlation functions, but there are E mode, B mode, like polarizations from CMB. It's little bit different from the temperature fluctuations. So we are expecting some more detailed observations from coming years. I mean, not from the James Webb, but there are other exciting observations out there.
So this polarization in CMB, when is it expected to come? And which experiment is planning to do this?
Actually, it's maybe you know about bicep experiment. It's a ground-based telescope, and it is measuring these polarizations of CMB. I don't know what exactly they measure. I don't think it's temperature. Maybe they're measuring the temperature, but by analyzing the temperature, they get some kind of polarization, the information about the polarizations in the CMB. So basically, these polarizations are originated due to some effect of gravitational waves, primordial gravitational waves. Yeah.
Mhm.
So actually, there was a claim by Bison some years ago that they detected these polarizations, and they claimed that that is due to the primordial gravitational waves, and they claimed that that is the evidence of inflation. But after the close analyze by some other people, they realized that this is not due to the primordial gravitational waves. This is due to some dust, the intergalactic dust.
Mhm.
So they just misunderstood the dust with the primordial gravitational waves, polarization due to the dust. So and yeah, so that was a kind of a fun thing happened some years ago.
Okay. So dust can be dominant. That means.
Yeah, they didn't screen, or they have some process, right, to screen this dust, so remove this dust. I mean, there are polarization coming from dust, but we have to model this dust and remove that polarization from the observations. But they have done it they have done incorrectly. So they didn't remove the polarization from the dust properly. So they got some kind of polarization. Then they assumed that, or they thought that that is the polarization due to the primordial gravitational wave. And there were lots of paper giving inflation, evidence of inflation.
Nice. Okay.
Yeah, actually 4 or 5 years back, multiple things happened, right? Actually, where like there were, like, I don't know, early conclusions were drawn and then they were later retracted in
Yeah.
this also, probably then something related with particle physics also. Yeah, I don't remember all of them now, but that was, yeah, that was interesting. But anyway, so right now the slide you are in, it is just giving me an weird idea here. But I think the image is like showing, and maybe you said it probably, the image is showing two rings here, the two white rings, and you have joined the two cones that start from there into one, probably. I don't know who created this art, but so is it kind of saying that, like, I mean, it is possible to have like this red epoch? It is possible to have like multiple starting points and they merge?
Multiple starting points and then merge.
So what we
Why do
see
we need
today
that?
is basically like, I mean, what we see today right now, we are thinking, oh, there was this one single epoch, and then there is like either going into the dotted green line or maybe expanding or whatever. But what if, like, I mean, you think of the purple color tunnel that you are creating, which is expanding, but you have two of them, right there?
Purple color, two of them.
Yeah, so you have this CMB in the background, like that's green, like, I mean, the blue-green. And then you have this, like, it's an imagery, like you have created an imagery of like, what is this? Like how it looks like.
What you're probably asking is, are they causally connected or not, right?
Okay. Yeah. These rings are basically causally connected regions according to whole Big Bang theory. Yeah.
Okay, so you are saying like one is before and another is after, like this is, I don't know.
No, these are different patches of the same plane.
Oh, so, okay. All right. Okay.
Just a schematic picture.
Yeah, I know it is a schematic, but that kind of gives an idea, right? Why do I have to think like just one of them? Is it possible that there are multiple of them and then they are coming and merging?
Okay, so I mean, I took this picture to explain this, the causally connected regions and things like that. I didn't explain those things that this related to this horizon problem of what Big Bang model and things. So yeah.
Yeah, I mean, that's totally off track. I mean, this comment is like totally off track. I know that, but just a thought.
Those were, I think, great discussions. I think we should stop at some time, I guess.
Yeah.
But this was nice, Rathul. Yeah, thank you very much. Yeah.
Thank you for the invitation. And
yeah, like I should mention that like we record this and put it, and your first video did get a lot of views on the, when I see it on the YouTube. So that's nice.
Yeah, maybe you can put a link to the new one when you post it. Post this one. Like
it is automatically posted, right? Usually whatever I record here, I automatically post it.
No, you will post it, but connect the two videos of his, like this is part 1 and part 2.
Oh, in the maybe about the video, I can put a link to that, right? Yeah, maybe. Yeah,
Yeah,
sure.
something.
Sure. I can do that. Yeah. Okay.
Okay.
Yeah, nice. Thank you again, Rathul. Yeah,
Yeah. Thank you.
hopefully you can give
And
more
Thank you.
such
Yeah.
nice talks. Yeah.
thank you, Tachi and Sajesh, and also other members of Sphics for
Yeah.
organizing and inviting me for the talk. Thank you.
Yeah. Welcome. Thanks.
I can see some people at Sphics there.
That's correct. Yeah. So that's Jupesh is there and Harikesh is there. So, and we have two, I mean, few people have started coming into Sphics, so that's kind of a nice sign. So slowly,
Students or
students actually. So we are starting to see some few students that are coming in. So from next week onwards, what I'm planning to do is that to address it to real students like 8th grade, 9th grade. So I'm thinking next week I will talk about an ellipsis maybe. So I'll try to draw an ellipse and maybe it will be useful for student like circle, ellipse, two ellipse, and maybe
Two
three
foci,
ellipse.
like a single foci, two foci.
Yeah. So I'm thinking that might connect well with 8th grade, 9th grade students. So, but because at least a couple of them have shown interest, so we'll see. Yeah, I'm also figuring out how exactly to connect.
so we are also doing like yesterday. We had some. No, today morning we had some presentations by our students. We were. I mean, we are training 23 MSc students.
Yeah.
For doing the MSc projects. So today, some of the students gave some talks. They just updated the progress, what they are doing.
Nice. And this is related to the Kerala Theoretical Physics Initiative, right?
Exactly.
That's a nice thing. So
Yeah, we frequently give talks, and talks in the sense mainly for now we are concentrating to train the students. So we give some talks on how to write CV things. And we gave one talk on how to write CV proposals kind of things, and another on how to write papers, like how to use LaTeX overleaves, this kind of thing. And next month we are giving on Python, like the use of Python and numerical computing kind of thing.
perfect. Yeah. Oh, that should be very useful. Yeah.
And we are meeting, I mean, this 23 students are under some 12 mentors. I mean, we don't say under, they are working with these 12 students, 12 mentors. And they are frequently meeting like once in a week or so.
Perfect. Yeah, I think it is a very good initiative. When I glanced through the website, I couldn't see all these details about the meeting every week and all that, but it was a great initiative, I think. Yeah. And like you had asked if I would be if I can give a talk. I think I can. It's just that I feel I'm not very qualified to for the opportunities available. I just feel I'm not qualified. So I can start with something else and then they can ask questions on that. That's the way I was thinking. Do you think
I
that?
mean, that's your convenience. Whatever you are feeling to, just we feel that just interaction would be good for our students.
Yes, exactly. That's what I would like, because I feel I'm not qualified because my applications never went through successfully. So I feel I'm surely not a great.
Just talk with students, and you are people will be excited and more interested
Exactly.
when the people talk with you, kind of very experts and people from outside, like from US, and send your associate professor from university, so people will be
Yeah,
very
exactly.
keen, very excited to listen to you.
No, I agree. I agree. I agree that yeah, discussions should be. I'm a big believer of yeah, discussions leads to motivations and so on.
Yes, yes.
Yeah, yeah. No, I agree. Okay, great. Yeah, so
Okay,
let
yeah.
us. Thank you again, Rathul.
Yeah, thank you.
And thanks everyone.
Thank you.
Yeah, bye. Good night.